In this video, I'm going to be describing how we can find the area between two curves. So we have two different examples that we might see. In this left example, to find the area between these curves, we could use vertical rectangles. To find the area between these two curves, we could use horizontal rectangles. And so I'll describe the difference between those two techniques. In general, you're always trying to take your greater function and subtract your lesser function. So what do I mean by that? Well, in here, if I take the area underneath this curve, it includes everything underneath the curve. But if I subtract the area underneath this bottom curve, then what I get is the in-between area, the area between the two curves. So on the left example, if we find the area underneath our f function from a to b, and we find our area underneath our g function from a to b, and I subtract the area underneath our g function from the area underneath our f function, then we get the in-between area. So we could do it that way, or we could use the property of integrals, which says that as long as I'm integrating on the same interval with two different functions, I can just subtract those two functions and then integrate. So it's kind of like thinking about distribution backwards. So if I distribute my integrand here, then I get this. So we're just thinking about it backwards. We can subtract our functions first and then integrate. Likewise, we could do that with our horizontal rectangles. And all we're doing differently is we're talking about functions that are in terms of y rather than in terms of x. So the exact same process, except that, and there's a typo. That should be dy right there, dy. Regardless of which type of integrating you're doing, whether you're doing it horizontally or vertically, it's going to be the same process. As long as we know which function is greater, whether it's the top function or the right function, and we just integrate that area and we subtract the area given to us by finding the area underneath the lesser function, whether it's on the bottom or on the left, then we get the area in between the two curves. So let's practice doing that. Sometimes we're given information that encloses the region that we want to find the area of. For example, if we are given the function y equals e to the x, that would be this function right here, exponential function. We're also given the function y equals x. That's that linear function represented right here on the bottom. And then we're given two vertical lines. So x equals 0 and x equals 1. And if we want to find the area that's bounded by all of those functions, then we're just trying to find the area in between right here. So what we can do is we can use these vertical functions, or vertical lines, not functions, to be the bounds of our interval. So I'm going to integrate from 0 to 1. And I'm going to integrate the area underneath this curve, and I'm going to integrate the area under this line, and I'm going to subtract this lesser function from my top function, and that gives me the area in between. So if we do e to the x minus x and then integrate, then we can solve for the area in between. So because we can't do anything to simplify this subtraction, we're just going to find the antiderivative. The antiderivative of e to the x is e to the x. Antiderivative of negative x is negative 1/2 x squared. And if we evaluate that at 1, then we just get e minus 1/2. If we evaluate it at 0, e to the 0 is 1. This becomes 0 over here, so we're subtracting 1. So this simplifies to e minus 1/2 minus 1, or e minus 3/2. We can represent it a couple of different ways, but that's the area in between those two curves on that interval, or the area bound to that region. Sometimes we're not given those boundaries. So what we need to do is find the intersections between our two graphs, or the intersections between two curves. To find the intersection between two functions, we just set our functions equal to each other and solve for x. So that would be our first step. We got to find the endpoints for our interval. And so we're going to set our two functions equal to each other to do that. So we're going to find the area between f and g. First thing we're going to do is set these two functions equal to each other to find their intersection points. In doing that, we find that the intersection happens at two spots, at x equals 0 and x equals 1. We could also plug these into a graphing calculator or use Desmos like I did here to visualize what we're doing. And so we can see that when we plug in these two functions, they do intersect at x equals 0 and x equals 1. And then we're going to try and find the area underneath our top function minus the area underneath our bottom function to find that in-between area. So now that we have our boundaries, we got our interval, we're going to integrate from 0 to 1. The second thing you want to do is figure out which function is the top function and which function is the bottom function. You can do that by plugging in a test value in this interval. So if I plug in any value in between 0 and 1, I should be able to tell which function gives me a bigger value and which gives me a smaller value, and that'll tell me which one is on top and which one is on the bottom. So I plugged in 0.5 into both of these functions, and I figured out that this function gave me a bigger output, and this function gave me a smaller one. So this is 2x minus x squared, and this is x squared. So now I know which function to subtract from the other. I'm going to do 2x minus x squared and subtract x squared, and then integrate. So when I do that, I get 2x minus 2x squared. I can find the antiderivative and evaluate it at the top and bottom limits of integration, and simplify it all and find the area in between our two curves. Let's do another example. What happens if we have a function that intersects at more than 2 points? Well, the process is still the same. We're going to find our intersection points by setting our functions equal to each other and solving for x. So when I do that, I find that my intersection points happen at 3 spots, at x equals 0 and at x equals positive and negative 2. And so we can plug these functions into a graphing utility and visualize it, and we can verify that we do have intersections happening at negative 2, positive 2, and 0. And we could also visualize the areas that we're trying to find. So this one that's curving in an S shape is our cube function. This graph right here that's an upside down parabola is our negative quadratic function. And so we got two different areas that we're going to try and find. This area, the pink one, and the blue one. And so we're going to set up two different integrations. So we got an integral that we're going to set up and evaluate that's in between negative 2 and 0. And then we're going to set up an integral to find the area in between 0 and positive 2. And we're going to add those two areas together. So let's figure out which function is on top and bottom, and it may differ depending on the interval. So on the interval from negative 2 to 0, the f function turns out to be greater, so that'll be on top. I plugged in negative 1 to test. The g function gave me a smaller value, so I know that's going to be on the bottom. And again, we can verify by looking at it. Negative x squared is on the bottom, x cubed is on top. So if I subtract the g from the f function on the interval from negative 2 to 0, we can find the area in between those two curves in that region, in that first region. And then if I subtract the f from the g function, because in my interval from 0 to 2, they get flipped, now the f function is on the bottom and the g function is on top. So if I integrate that from 0 to 2, I get the area of that region. If we simplify all that, we get 24. Running out of time in this video, so I'll continue in the next one.